Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, this is the Regression. I, as the first speaker of this work, will present you about Industrial Statistics 2. The title is Simple Linear Regression and Correlation. And this is the members of our group. For the first is me, Fikri Mahasin Rivani. Serial number is 1810932038. And there are three other members, and they are Taufik Alfandiheldy and Fadel Veromisa and Qodratul Khairi. So we come with simple linear regression. Regression analysis is used to first predict the value of a dependent variable based on the value of at least one independent variable. Second, explain the impact of changes in an independent variable on the dependent variable. Dependent variable is the variable we wish to predict or explain. Independent variable is the variable used to explain the dependent variable. Simple linear regression model. First, only one independent variable, it is x. The relationship between x and y is described by a linear function. Changes in y are assumed to be caused by changes in x. And the formula is ye equals to beta O plus beta 1 xe plus e1. And the information is ye is dependent variable, beta O is population y-intercept, beta I population slope coefficient, xi is independent variable, and ae is random variable. And we can see from the graph. And for the formula of y is y equals to bo plus bi x. The information is y is estimated or predicted y value for observation, bo is estimate of the regression intercept, bi is estimate of the regression slope, and x is the value of x for observation. So we come to the method of least square. To find bo and b1, the estimates of beta O and beta 1 so that the sum of the squares of the residuals is a minimum. The residual sum of squares is often called the sum of squares of the errors about the regression line and is denoted by SSA. This minimization procedure for estimating the parameters is called the method of least squares.
Next, this is the formulas in the method of least square. Next, the properties of the least square. The first one is mean and variance of estimators. In what follows, we show that the estimator B1 is unbiased for beta 1 and demonstrate the variances of both B0 and B1. This will begin a series of developments that lead to hypothesis testing and confidence interval estimation on the intercept and slope. And the second one, partition of total variability and estimation of variance. To draw inferences on beta 0 and beta 1, it becomes necessary to arrive at an estimate of the parameter variance, appearing in the two preceding variance formulas for B0 and B1. The parameter variance, the model error variance, reflects random variation and experimental error variation around the regression line. The third one is the estimator of variance as a mean squared error. And then this is the formulas of estimators of variance.
Of correlation and determination. First, the correlation coefficient, which is symbolized by R. As you can see here, the mathematical formula for computing the R is this. So R equal to n sigma xy minus sigma x multiplied by sigma y over root of n x square sigma minus sigma x square multiplied by root of n sigma y square minus sigma y square. The quantity R, called the linear correlation coefficient, measures the strength and the direction of a linear relationship between two variables. The linear correlation coefficient is sometimes referred to as the person product moment correlation coefficient in honor of its developer, the Corelation. Next, the coefficient of determination, which is symbolized by r square. So as you can see from this symbol, the coefficient of determination is just the square of this one, of the correlation of coefficient. So you just need to square the result to find the coefficient of determination. So the coefficient of determination, or r square, is useful because it gives the proportion of difference or fluctuation of one variable that is predictable from the other variable. It is a measure that allows us to determine how certain one can be in making prediction from a certain model to graph. The coefficient of determination is the ratio of the explained variation to the total variation. The coefficient of determination is such that 0 less than equal to r square and less than or equal to 1 denotes that the strength of the linear association between x and y.
Okay, so I will explain about the assessing the utility of the model, making inferences about the slope beta 1. Refer again to the data. Suppose that the x variable is completely unrelated to the y variable. What could be said about the value of beta 0 and beta 1 in the hypothesized probabilistic model y if x contributes no information for the prediction of y? The implication is that Ey equals to beta 0 plus beta 1x does not change as x changes, regardless of the value of x, always predict the same value of y. In the straight line model, this means that the true slope beta 1 equals to 0. Therefore, to null hypothesis. The null hypothesis h0 beta 1 equals to 0, which means that the x contributes no information for the prediction of y. The alternative hypothesis is that beta 1 does not equal to 0. X does contribute information for the prediction of y. If the data do support the alternative hypothesis, we will conclude that x does contribute information for the prediction of y using the straight line model, which means that the beta 1 does not equal to 0. The appropriate test statistic is found by considering the sampling distribution of beta 1 hat, or the beta 1 sample, the least square estimator of the slope beta 1. The least square estimator of the slope will be normal distribution with mean, the true slope, and standard deviation. The standard deviation for beta 1 is sigma divided by SSXX. Since sigma will usually be unknown, the appropriate test statistic will generally be a student's t-statistic formulated as t equals to beta 1 hat minus hypothesized value of beta 1 divided by sigma beta 1 hat. where sigma beta 1 hat equals to sig s divided by square root of ssxx. If we substitute the sigma beta 1 hat to the t formula, then we get t equals to beta 1 hat divided by s divided by square root of ssxx. Thank you.
Next, our topic is about estimation and prediction. We have two conditions in here. First is 100 multiplied by 1 or minus alpha percent confidence interval for the mean value of y at x equal to xp. As you can see here, the formula is yp hat plus minus a over 2 multiplied by s root of 1 over n plus xp minus x hat over ssxx, where xp is a particular value of x that lies in the range of x values in the sample dataset used to construct the least square regression line, and yp hat is the numerical value obtained when the least square regression equation is evaluated at x equal to xp, and the number of degrees of freedom t alpha a over 2 is derivative of f equal to n minus 2. Next, the second condition is 100 multiplied by 1 minus alpha percent prediction interval for an individual new value of y at x equal to xp. yp, where the formula is yp hat plus minus t a over 2 multiplied by s root of 1 plus 1 over n plus xp minus x hat square over ssxx. So the difference from before is this 1 in here and there is square in here, where xp is a particular value of x that lies in the range of x values in the dataset used to construct the least square regression line, and yp hat is the numerical value obtained when the least square regression equation is evaluated at x equal to xp, and the number of degrees of freedom for t a over 2 is derivative f equal to n minus 2.